where it worked earlier. So let me fix this issue. Give me a moment. Let me start share and try again. How about now?
Still not
Still
in
no?
presentation.
How about when I swap display? No. Huh. Maybe.
Or would you mind just proceed with your normal mode?
Or how about I try to share the screen, the whole
Just
screen
we see the
instead.
screen.
And how about now? How can I can swap display.
It's your present.
Yeah,
Oh,
it's
okay
now. It's okay now.
Yeah.
Yes.
Thank you. Sorry for the wait with the technical issue. Yeah. Hey, thank you again for having me here. So like Guojun just introduced, my name is Chiao-Hsuan Wang. I'm currently a postdoc working at the University of Chicago. And for today's talk, I'll be presenting our recent work on the generalized matching condition to achieve quantum transduction with unity conversion efficiency. And this work is a joint work with my advisor, Liang Zhang, and another postdoctoral researcher from our group, Mengzhen Zhang. I'd like to start with a broad overview of my research interests. So like all the people in this meeting room, I've been working on quantum information science and technology. My experience have been centered upon quantum information theory with bosonic systems. So conceptually, using bosonic system for quantum information and computation is a lot different from using qubit-based systems. So first of all, compared to the qubit system, or qubit system, they only have finite discrete levels. But for bosonic system, a single bosonic mode, its states can be described by the infinite dimensional ladders in the harmonic oscillator. So one bosonic mode already have a huge complexity that also brings us new opportunities. For example, one can utilize this infinite dimensional Hilbert space to do quantum error correction, such that by encoding and storing quantum information inside the states of this harmonic oscillator ladder, one will be able to restore and correct quantum information in just a single bosonic mode. So that in contrast to qubit-based error correction scheme, then they would actually require several qubits in order to store 1 qubit of information. Or for bosonic system, you can just use a single harmonic oscillator to achieve that. And in fact, people have realized quantum error corrections in the bosonic system that reach the break-even point. So in 2016, and at the experimental group at Yale, they have successfully extended the lifetime of their quantum information by storing them inside a microwave photonic cavity in the superconducting devices. So that is a really great achievement. And another reason I'm interested in photons that for quantum information processing is because of recent experimental advancement that there has been a lot of great efforts in building really high quality resonators, especially photonic resonators in both microwave and optical domains. So like in superconducting devices, the microwave resonator is actually longer lived than the superconducting qubit system. So based on these motivations, I've been working with my collaborators on how to control and manipulate bosonic systems for quantum computation. And we have work on how to use the auxiliary qubit modes to control the bosonic mode and by generating photon number dependent Hamiltonians. And boson can also come in a very helpful way for quantum simulation. So because of the complexity of the Hilbert space for a bosonic system, it is really difficult to simulate using a classical computer. And that means for using quantum study of the dynamics of bosonic system, one can see the advantage of using quantum system really easily. So the most natural platform to study the dynamics a bosonic system is to use another controllable bosonic system to emulate its evolution. So this is called the idea of quantum simulation, first proposed by Feynman. During my PhD, I've worked on a different scenario for photonic system, specifically to study photon thermalization in driven open quantum systems. And for today's talk, I'll be talking about another application for bosonic system in quantum information theory, that is for quantum communication. So the photons are the natural carrier for quantum information because it can move easily in both free space and in waveguides. And especially if you propagate the photons in optical fiber, you can actually have really low loss across long distances. So this is natural to think of bosonic modes for quantum communication. In addition, again, owing to this infinite dimensional Hilbert space of a single bosonic mode, one can in principle transmit infinite amount of quantum information in an ideal scenario using just single bosonic mode, which is something that one couldn't do using the work I'm going to present today is motivating by the application to build quantum networks. So by networking quantum devices, one may be able to do distributed quantum computation by connecting local quantum processors. Or eventually, one might be able to realize a global quantum networks that one can transmit quantum information across the world and even do encryption, etc. However, this task is really challenging. It not only requires low-loss quantum communication across long distances, but on the same time, you also need to have high-fidelity quantum operations for all of your local. Single quantum platform that can realize these two criteria simultaneously. Therefore, people are looking for a hybrid approach instead. So for a hybrid approach, one would like to link different quantum components. For example, one can use optical system for example, using optical fibers for low loss communication and use microwave systems or other quantum computing device like quantum dots or like your ion traps for the quantum operations. That's already showing a lot of high fidelity processors available. So if using the hybrid approach, one will be able to harness the advantage of different quantum components and finally realize this goal of building quantum networks. So to build quantum networks, there is a key element that's called quantum transducer. The quantum transducers are the devices that allows one to coherently transfer quantum information from one form of energy to another. Like for example, if we use one might be able to connect the information from the microwave domain to optical domain coherently and to build a link with hybrid quantum network with optical communication and also microwave processors. So this is the motivation behind our work. And there are a lot of different approaches to realize microwave-to-optical transduction. And here I'll be focusing on the transduction scheme using linear conversion, which means that we'll be looking at a scheme that will be converting the signal or the information from one state to another. In compared to there are also other schemes such as using entanglement between the system and then do quantum teleportation. That will be out of scope from today's talk. So for linear conversion scheme, one have to find an appropriate physical process that can reach this huge energy difference between the micro and optical frequency scales. So there are different ways to achieve that. So major approaches include directly convert a microwave to optical signal via chitin material in electro-optic devices. Some other approaches may utilize an intermediate mode to bridge such conversion. So for example, in the electro-optic mechanics experiment at GILA, they will utilize a membrane mechanical mode to bridge the conversion between a microwave mode and then couple the membrane mode with the optical mode using optomechanical interactions. And my collaborator at Yale and I will also work on using magnons as the intermediate stage to bridge the conversion. And more recently, there are some proposals that the process is more complicated because they might involve 2 or even more intermediate modes. And those efforts are usually based on atomic levels. And the reason that people are interested in looking at using atomic systems for transduction is that one might be able to have a large atomic ensemble to enhance the coupling between the systems. For conversion using 2 intermediate stage, one example is using rare earth ions that they have both the micro and optical transition. So to reach this conversion, one would convert the microwave signal to a microwave excitation level and then drive it to coherently excited to another optical level, and that will finally couple to the optical mode for the conversion. There is even more complicated scenario using 6-wave mixing processes in the rare earth atoms. So despite all these different efforts, this microwave-to-optical transduction is still really challenging. And in fact, none of them has been able to work in the quantum domain yet. So to be able to transfer quantum information using transducers, there are requirements such that it has to have really high conversion efficiency. So the ideal conversion efficiency is the fraction of quantum information that can be successfully converted from your input signal to your output signal. And for the ideal conversion, this eta should be 1, which means that all of the information has been successfully converted to the output port without loss to the noisy environment. And for the transduction to be quantum without any post-processing through this linear conversion scheme, there's a threshold that eta has to larger than 0.5 in order to transfer non-zero quantum information. And the physics behind this, one can use no-cloning theorem to understand this threshold. So if the conversion efficiency is less than 1/2, it means that more than half of the information has been lost to the environment. So if one will be able to recover the states from this less than 1/2 conversion efficiency, then the environment will also be able to generate another copy of your original quantum information. And this will violate the non-cloning theorem, and therefore, there's this eta larger than 0.5 threshold. And one can see that.
Chiao-Hsuan,
Hi.
may I ask a question?
Sure,
yes.
Please.
So in the previous slide, you give the definition for the transducer, and it said coherently transfer the excitation or the energy to another form, right?
Right.
But
right.
in this case, when your eta is less than 1 usually, then
yes.
how you call it a coherent process? How can it be called a coherent process? That's my question.
Right. So if it's just like this linear conversion, I think the answer to this question is that if you want to preserve your quantum coherence without any post-processing, then you have to have efficiency larger than 1/2.
Okay.
Yeah. So if you have efficiency larger than 1/2, then you can still transfer some amount of quantum information. So this can be understood like using the quantum channel theory. So like in the ideal scenario when eta is 1, you can actually transfer infinite amount of quantum information using that single bosonic mode, actually. Yeah. Now this threshold is to have some non-zero quantum information communication. Thanks for your question, Junda. And another criteria to achieve quantum transduction is that we need to have low added noise, so that one will be able to resolve the signal from the background noises. So if you look at this value for the current state-of-the-art quantum transducer for microwave-to-optical system, you can see that none of them has surpassed this threshold. One may be one might use some post-processing to increase this threshold and to transmit quantum information, but that actually costs a lot of resources. And for this electro-optomechanic system, although it's near the threshold, but they are suffering from a huge, larger amount of added noises in this scenario. Okay, so for the work I'm going to present today, we're working on a problem to how to design the parameters of these different transducer systems in order to achieve the highest possible conversion efficiency. So from that, it brings us to the outline of today's talk. First, I will present a systematic study that using a model for the quantum transducer that will model the quantum transducer process as a bosonic chain with an intermediate mode. And quantum transduction is achieved by injecting a signal through one end of the mode, and it will propagate along the bosonic chain and finally retrieve at another external channel coupled to the B mode. So starting this transducer model that covers all the leading platform that I just mentioned, introduced earlier, we like to study how to design the system parameters in a way such that one can reach a conversion efficiency equals to 1. And that criteria among the physical parameters of the system to achieve unity conversion efficiency is called the matching condition. And the matching condition we found will be the generalized one in compared to what people found before. And we also have established an effective circuit model that reproduce the same frequency response as our quantum transducer, which can substantiate our understanding of the generalized matching condition. Okay, and please feel free to stop me along the way if you have any questions. So let's start with a general model of quantum transducers. So I would like to take the zero-stage conversion, that's the simplest case, for example, to demonstrate how this kind of process is. So for electro-optic devices for conversion, people would couple in some external signal at a frequency omega n and couple that to a microwave cavity at a frequency omega a. And this mode would have some broadening due to its dissipation. And then using the chiral material, by driving this with the laser field red detuned from another mode, omega b, one will be able to reach the conversion from this excitation inside this mode A to the mode B. The mode B is at another frequency, omega b, which can be an optical frequency in this scenario. And then this mode B is coupled to another external channel, and then finally will output a signal at the external port. So this is the frequency diagram in the lab frame for these different modes. So if you take a closer look at the interaction that allows this conversion, it's actually originated from the three-way mixing process that we would be able to use input one excitation from the A mode and also the pump frequency, pump laser mode, and annihilate these two to create a B mode at another optical frequency. So if we work in the strong pump limits such that we can actually approximate this laser pump as some oscillating classical field, then we can write down the C as some square root of NC, which is the mean photon number for the pump and times some oscillating frequency. Then one would arrive at this effective time-dependent parametric interaction between the mode A and B. So if you want to move to the rotating frame, the beep to the rotating frame along with this laser drive frequency, one actually arrive at a time-independent Hamiltonian that is a beam splitter interaction between the A and B mode. So this type of interaction you can understand it as A and B, they are swapping their excitation. So by swapping their excitation, this helps us bridge this propagation of quantum information from one mode to another. And more generally, the conversion might involve an intermediate mode, and we will call that an N-stage quantum transducer in the setting. And we model the quantum transducers as a Bosonic chain that will have beam splitter coupling with this nearest neighbor mode. And then they are coupled to two external channels for input and output signals. So studying this model, the next question we would like to ask is, what's the function of conversion efficiency based on these physical parameters inside this Bosonic chain system? So for this, I'd like to show a brief example about the conversion efficiencies calculation. So again, I'm using the zero-stage conversion as the simplest example. And for zero-stage conversion, the Hamiltonian in the rotating frame, we can write it down. For the A mode, have some detuning delta A, and B mode have some detuning delta B. And we have beam splitter interaction that's swapping the excitation between the A and B mode. With the Hamiltonian and along with the input and output formalism, we can write down the equation of motion for this A and B mode, that they will have their some energy and dissipation turned off its on, coupling to the G mode, to the other mode, and also the coupling to the input and the input modes. We will have consider both the input from the external port, that's the signal, and also some intrinsic losses because of the environment. We can then do the Fourier transformation for this equation of motion, so we'll be working in the frequency domain. To combine this lane-driven equation of motion with the input-output formalism that shows the relation between the input-output mode and the intracavity mode A and B, one can solve for the scattering matrix between the A in, A out, B in, B out. So from this scattering matrix, this defines our conversion efficiency, which is the efficiency of the photon number power transferred from one port, external port, to the other. So for conversion that with the input from the A mode and then output at the B mode, the conversion efficiency is defined as the square of the scattering matrix element from A in to external to A out external. And since our system, the coupling is reciprocal, so for this side of the scenario we're considering for the talk today, the conversion efficiency from one end to another will be the same as the conversion efficiency from the reverse direction. So here, I'd like to just show some explicit example of the conversion efficiency. So this is the zero-state conversion efficiency appropriate for electro-optic devices. We'll have some prefactor. This shows the amount of information that can be successfully converted to the output port when they are leaving the A and B mode. And we have another additional expression here that comes composed of other physical parameters inside your Bosonic system. And here I also listed down the one-stage conversion efficiency and a two-stage conversion efficiency. You can see they actually have a nice structure, even though they got more and more complicated when the intermediate modes get increased. So here we summarize the general formalism for the N-stage quantum transduction. So for this N-stage quantum transduction model we just described, the Hamiltonian is given by the mode energy of each mode at some detuning in the proper rotating frame, and also the beam splitter interaction between your neighbor mode. And this is the general form of its conversion efficiency. So this overall conversion efficiency tells how the fraction of information can be converted from this input signal port to the output port. And we can separate this expression into the external efficiency and the internal efficiency part. So the internal efficiency part you can understood as if you are now treating all the modes, including the input modes from the external channel as well as from the intrinsic loss environment together as some A in and A out that couple to the A mode at the total rate kappa A. And then similarly, another B in and B out for kappa B. So this internal efficiency will be the scattering matrix for this A in, B out, and B, sorry, A in and out and B in, B out. And so this internal efficiency only cares about the parameters in the middle. So for the external efficiency, this is the fraction of information that after leaving the cavity of the A or A and B mode, and how many of them can be successfully converted to the external port without losing to the noisy environment, kappa AI or kappa BI. And this prefactor is independent of number of stages. And when there's no loss for kappa AI and kappa BI, this prefactor can be set to be 1. Okay, so what's the system? And the internal efficiency can be written as this form. In the numerator here, we have square root of kappa A, kappa B, which are the total dissipation rate of A and B mode. And we have the product of all the coupling rates within the bosonic chain. In the denominator, we have a polynomial function in the frequency and other parameter, just given by the determinant of this n+2 by n+2 matrix. The diagonal elements of these matrix are the mode susceptibility. So this is the susceptibility of mode tells how each mode will respond to the external input or output. And for first of diagonal axis, we have I times G. So from now on, I will use this new J, that's omega plus delta J for each mode, which will be the relevant frequency, a component for the mode, which is this number is invariant even if we shift the system over some overall frequency scale. So the next question is, now we have this formulation that tells us how the efficiency depends on the system parameter. Then the next question would be how to achieve eta n equals to 1 by designing our system parameters in a non-trivial way. So now we're looking at a condition such that we can have unity conversion efficiency. This can be achieved by assuming that system is lossless and also setting this internal efficiency part to be 1. And the criteria to satisfy this unity conversion efficiency is called the matching condition. So again, we use the simplest zero-stage case for example. So previously, the matching condition people found is given by this. So when the cooperativity between the two modes defined as 4G squared over kappa A kappa B equals to 1. But this matching condition is actually relied upon another implicit stringent assumption that all the modes has to be resonant, that nu A and nu B all have supposed to be 0. So here we're asking the question, is this the most general solution? How about when we have extra coupling? When we have stronger coupling, we should be able to still get here to get eta efficiency to be 1. So, and we actually find there are extra solutions in the strong coupling regime. So if we set these zero-stage internal efficiency to be 1 and solve for the relevant frequency for the A mode nu A, we will get two independent criteria. And alternatively, we can solve for nu B instead and get another set of criteria. And these two sets of criteria, they are mathematically equivalent. And we found that it's also this criteria is also equivalent to another set of criteria by solving for zero reflection, and actually a zero internal reflection on the optical or the microwave side. So the two independent criteria given by this zero reflection condition is in a symmetric form in A and B. And we can see that this is direct generalization from the previous matching condition. And the previous explored matching condition is just a special case that all the detuning, though the frequency has to be 0 in order to satisfy this equation. So now we have the mathematical formulation available. And the next question we would like to ask is, and how can we understand these? And we've found that this actually, we can understand this using the same interpretation as the impedance matching condition for electric circuit, and is given by the maximum power transfer theorem. So in the electric circuit, if you have some active voltage acting on a source impedance, and it's been known that in order to transfer maximum power to another load impedance, it had to satisfy this matching condition such that the load impedance has to equal to the complex conjugate of the source impedance. So this impedance matching condition, if you actually give rise to two criteria, as we have here. So its real part will give rise to resistance matching, and its imaginary part will give rise to a resonant condition for the system. And we found out we can actually interpret our transducer system in a similar way. If you look at from the A mode's perspective, and before it couples to the B mode, it would have its own susceptibility that shows how it will react to the external input or output modes. And when it coupled to the B mode, we will see a modification to the inverse susceptibility of this A mode given by G squared chi2. Chi2 is the original susceptibility of the mode B. So looking at these two equations, we can directly see that this the first line here show the relationship between the imaginary part of this chi A inverse and this G squared chi2, right? So inverse of this chi, imaginary part of this chi inverse should be equal to minus imaginary part of this G squared chi2. And the second line, the similar is just taking the real part to be the same, which suggests that this first expression is just the resonant condition, like an impedance matched electric circuit, while the second line is the resonant condition, the resistance matching condition that match the resistance of the A and B mode. Okay. So from that, we can extend this interpretation of this matching condition and look for the general criteria to get unity conversion efficiency for this N-stage conversion stage. Stay with me so far. So before jumping into the generalization to N-stage, I would like to dig further into what we can do with this extra degrees of freedom for non-resonant frequencies. So now we'll be able to work in at the non-resonant regime given the generalized matching condition. So let's first look at the all-resonant case for the zero-stage conversion. So for zero-stage transduction, this is the energy diagram, again, in the left frame. So the previous all-resonant condition actually means that in order to get the perfect transduction, the input signal has to be resonant with the first bosonic mode A, such that omega I equals to omega in. And on the other hand, the output sigma mode also has to be resonant with the output bosonic mode, the end bosonic mode omega B, in order to achieve perfect conversion. But this criteria has now been lifted by the generalized matching condition we have here. So with the generalized resonant condition, we can now have non-zero news as long as they satisfy this relation. And we also have the generalized we would have some effective cooperativity. It is modified by the non-zero frequencies nu and nu v still equals to 1. So what we can do here is that now we have this extra tunability of the system. So for example, if one can enhance the coupling strength between the system and also change the frequency of the pump as well as input signal frequency. Now I'm be able to output a signal, but still at the unity efficiency, even if it's not resonant with the B mode. So that will give rise to extra tunability and working region for the transducer devices. I'd like to also note that although we have this non-resonant condition, but the energy in the system is still conserved. So this is given by the fact that when we look at the input signal and output signal, we will always satisfy this relationship that omega in plus omega pump should be equal to omega out. And this is because we're all working at the same frequency, but for B out working in the rotating frame. So I'd like to next generalize this discovery to general end-stage conversion scenario. And actually, to establish this rigorous interpretation of impedance matching, we've been able to found a set of effective circuit model such that this effective circuit, if you look at the power transfer efficiency, it can actually replicate the same power transfer efficiency as our photon number conversion efficiency. This correspondence can be achieved by identifying this non-trivial relationship between the parameters of our transducer system and also the elements in the effective circuit. So from that, we'll be able to write down this generalized end-stage impedance matching condition. So a recap of what we have learned is that it's possible to achieve ideal conversion such that we will have unity conversion efficiency when the system is lossless. And also, the system will have impedance matched parameters inside the system. And it's also equivalent to having zero internal reflection along the way. And this is also analogous to the electric circuit maximum power transfer theorem, such that when a system, when a power transfer is impedance matched, there will be no reflective power wave in that scenario. Okay, so for this end-stage case, we can write out the correspondence to the impedance, which will be inverse of its susceptibility for the mode, and then we will match that to the effective, the modification to its susceptibility because of coupling to all the other modes. So this is written down, can be written down in this expression, just like in the impedance matching circuit, that we will have some V1 complex conjugate equal to all the load, that is the Z2 effective here. And we further simplified it into this metric determinant form that we can write it down in terms of this tridiagonal matrix for any M mode. And the real part of this expression, we call it the generalized resistance matching. And it's the imaginary part of this matching condition, we call it the generalized resonant condition. And what we call it generalized is that it is in the sense that we can have non-resonant frequencies such that we can have tunability in different detunings and also a different this new eyes. And these tunability frequencies actually correspond to purely imaginary resistors that we introduce in the effective model. So in the real world circuit model, there's no such imaginary resistors because resistance has always to be real. So we are generalized in the sense that we now have this non-resonant frequencies corresponds to the peripheral region that people haven't previously explored in the quantum transducer community, and also correspond to something that's not available in the electric circuit. So before going to summary, I'd like to show the last example and to demonstrate the fact that this matching condition in the presence of loss, one can no longer achieve ideal conversion. One can still use this interpretation of impedance matching to find what's the optimal parameters to get the maximum available conversion efficiency. So we will look at the case for one-stage conversion. We first assume that kappa 2 to be 0. Then we will be able to write down the generalized matching condition for the one-stage case. And we see that it's direct extension from the matching condition people previously found under the all-resonant assumption. So again, we can write down to an effective circuit for the mode. So for one-stage conversion, we will have the A mode can be the microwave mode, and this middle mode can be the mechanical mode or the magnetic mode, depends on your device. And then finally convert that to the optical modes that will couple to the output port. So we can again write down an effective circuit model that allows one to connect the impedance of the mode with a one-to-one connection to the elements in the circuit. So for now, look at the case with lossy intermediate modes. So when kappa 2 is non-zero, since there is a loss within your transducer, then it's impossible to achieve unity conversion efficiency. However, we can still look at the scenario and try to optimize your parameters and to find what's the highest achievable efficiency that one can get. So here we view from the middle mode point of view. We can write down an impedance for the middle mode. And the coupling to the A mode will give rise to an effective impedance for the A mode and for the B mode respectively. And I will choose from the middle mode point of view so that it will be symmetric in A and B. And look at the real part of these, it will give rise to its resistance, and also imaginary part give rise to their reactance. One can see immediately from this form of resistance that when the system is at resonance, we would have a maximum available resistance for the A and B mode. So when taking nu A and nu B equals to 0, we will have this RA max, RB max, while R2 is unaffected by the detuning for A and B mode. Okay. So if we normalize this R respect to R2, which equals to kappa 2 over 2, we can actually have a comparison between the cooperativity of between the A mode and the second mode, the middle mode is actually normalized to 1, and also compared to the cooperativity between the mode 2 and mode B. So given this comparison, those cooperativities of the system is usually limited by the experimental design, because the kappas and the G's is usually something that is fixed or limited by your experimental fabrication. However, the frequency and detuning is something that might be able to tune using by changing the laser frequency of the system. So now, given the value of CA, CAB, and CA2 and C2B as some fixed value, we can now look for using this nu A and nu B and nu 2 as our optimizable parameters to look for the highest achievable conversion efficiency. And find that there are actually two different parameter regimes. So when one of the modes is overcoupled in compared to another, say when the microwave mode is overcoupled in compared to the optical mode, such that CA2 is larger than C2B plus 1. That corresponds to this max resistance at resonance for this RA max is larger than the summation of R2 plus RB max. Then in this scenario, we found that it's actually helpful to add some non-zero detunings to reduce the resistance of mode A, such that it can match the resistance of the summation of the other two. And this is, in this scenario, we will have RA equals to R2 plus RB max. And we can treat Z2 and Z altogether as your load. And the maximum efficiency is achieved when the load impedance is a conjugate match to our source impedance. But the efficiency is no longer 1 because of this internal loss. And the maximally available efficiency in this case is limited by the smaller cooperativity of the two. On the other hand, when there is no mode overcoupled in compared to another, such that the difference between the cooperativity is less than or equal to 1, there's no reduction needed. So conversion efficiency is highest when the modes are all resonant. So this can again be interpreted as some kind of impedance matching, such that one can actually cut this middle mode's resistance into 2 different portions, and to combine one portion with the source and combine another portion to the load. And then one can be able to write down this equation that match the resistance of the source to the load, and that give rise to this maximally available conversion efficiency. So finally, here we are illustrating how we can tune this off-resonant frequencies, and in some scenario that off-resonant frequency can achieve highest possible conversion efficiency. Like I mentioned in the one-stage scenario, we would like to treat the cooperativity to be some fixed constant because they are limited by the experiment. And then we will look for, under the fixed cooperativity, we look for the optimal choices of frequencies, nu, j's, in order to achieve highest possible conversion efficiency. So for the 0-stage case, it's not surprised that would again see that when CAB is larger than 1, the conversion, optimal conversion is achieved with non-zero detunings. And for the 1-stage transduction case, again, it's just as what we have discussed before, that we will like to add some non-zero frequencies to the overcoupled mode in order to reduce its resistance such that it will match the combination of the resistance from the middle mode and the other mode. For 2-stage or more stages scenario, it's more complicated, but we can still, using this semantic study of impedance matching of the modes to complete this phase diagram and to identify different regions where off-resonant frequency can actually help our conversion. So in summary, I've demonstrated a general formalism to systematically study end-stage quantum transduction. And such formalism applies to all the major approaches for microwave-to-optical transduction. And by studying the function of conversion efficiency, and we like setting that to be 1, we found that ideal conversion is achieved when the system has impedance match parameters and also correspond to 0 reflection. And the limitation for ideal conversion is intrinsic loss. When there's non-zero intrinsic loss, the highest achievable efficiency will be reduced from 1. And from that, we've laid out the generalized impedance matching condition that its real part give rise to the generalized resistance matching, and its imaginary part give rise to the generalized resonant condition. And these extra parameter regimes of non-zero delta nus give rise to new possibility beyond the previous all-resonant condition. So first, we can have enhanced operational regime. For example, one might be able to tune the coupling and the frequency of the drive to have conversion efficiency that's not fixed to just a single peak. And then we've also seen that the conversion efficiency can be enhanced by adding some non-zero nus when there's intermediate loss and when one mode is overcoupled and compared to the other. And the manuscript of this work should be available on arXiv soon, and actually next week, if things proceed ideally. And I'd like to thank you, acknowledge my funding resources, and thank you all for your attention.
Okay, thank you.
Thank you.
Guojing. Is Guojing there?
Yeah, can you hear me?
Yeah.
Yes.
Okay, so anyone have any questions? Okay.
Yeah, I have one. Okay, so the efficiency is frequency dependent in general?
Yes, it's frequency dependent. Yes.
Yes. So if somehow if you input a photon and photon is shaped, so maybe it could have multiple frequency or frequency band, right? And in that case,
Right.
how to define the efficiency in your setting?
Right. So in that scenario, then each different frequency will actually correspond to different conversion efficiency. Yeah, thank you. It actually is a really great question, and that leads me to a little sneak peek about my March meeting talk. That's actually touch base on the question you just asked. So like you said, we can have conversion not just using a single frequency, but some range of frequency, right? So and for the transducer, one would like it to have desirable features, not only have high efficiency, low noise, but also large bandwidth, so that you might be able to convert a broadband of signal, like if you treat different frequency as independent channel, so that you can transfer more quantum information at the same time. Okay. So here, for
Sure.
multimedia talk, we will be able to, we're addressing the question, like for example, if you have low efficiency but broadband transducer versus a narrowband but high efficiency transducer, then how do we compare the two, right? How do we compare their performance? And the answer to that question is that we use the concept of quantum capacity. That is the maximum achievable quantum communication rate for that device. That, like you mentioned, we can actually have different frequency modes and then convert independent channels at the same time. And this value of Q will tell you the maximum amount of quantum information communication rate that can be achieved with this transducer if you can utilize all the across all the frequency spectrum.
So does this mean the narrow band is higher than in frequency compared to the broadband?
If you look at these two graphs, but it will
Okay.
depends on what's the detail of your system.
I see. Sure.
Yeah, you can even have like not just one peak. You can have several peaks for your transducers as well.
I see. Thank you.
Yeah, thanks for the question.
And is there any questions?
I may have some simple question. Since your model can be applied to many different physical systems, so do you have some value, numerical value in different system presentation? Example, like.
Yes, so are you follow up on this? Are you follow up on this capacity, or are you asking about the efficiency, conversion efficiency?
Since your system can be applied like to different electrical to optical, so in that case, all these parameter range are suitable for the specific physical system. Do you have any example?
Yeah, so if you're asking about the conversion efficiency, here are like the reported value that they have for their system. And they're quite consistent with the parameters that people typically study before. Yes.
I see.
Yeah, but I think another applicability to, especially for these two or intermediate mode stages. Since direct conversion and the one intermediate mode case, people have explored its matching condition, though in the all-resonant region. But for two or more intermediate modes, they don't have a systematic study of their matching condition. So we will be able to, our work might be able to apply to their system and to tell them what's the best frequency or detunings to be able to realize in their system. Yeah, but we haven't applied it like to the scenario, but in principle, yeah, if they have this they give us the experimental parameters, we'll be able to find what's the best the frequencies.
Yes, another question, you usually do it in the rotation frame. So usually, what's the frequency you are referring to for this rotating frame?
Okay, so the rotating frame, the reason I'm working with rotating frame is because we will need to have some nonlinear underlying nonlinear process to bridge the energy difference, right? Yes. So for example, in this like zero state conversion case, then the rotating frame will be the B mode, and the B output mode will be rotating at the same frequency with the pump. That is the pump that mediates the conversion from the microwave to the optical frequency. So this pump frequency should be at some frequency close to the energy difference for the B mode and A, between the B mode and the A mode. Yeah, so I would say it will depend on which rotating frame you are working at. So if we are working in like for zero stage case, you will be working in this rotating frame. Then in this scenario, the delta B will be equals to the pump frequency minus the omega B frequency. And the detuning for the A mode will be correspond to minus omega A in this formalism.
Okay, thank you.
Yeah. I'd like to also know that if you have some chain, if you're not doing quantum transduction for different frequency, like for example, you just want to transfer quantum information from one end to another without any frequency change, you can also apply this model to the scenario that everything is in the lab frame, because there won't be any time-dependent components in the system. Thank you for your question.
Yeah, thank you.
Is there any questions, further questions? Okay, if no, let's thanks Chiao-Hsuan again and give us a very nice talk. Thank you.
Thank you.
OK，好的，谢谢，好，拜拜。
OK， 谢谢，拜拜。
谢谢。
好，谢谢，拜拜。
拜拜。所以我们这边就。